So last time we were talking about quotients of one variable polynomial ring with coefficients in a field f. We recall that fx is a PID, which means that every ideal is generated by a single polynomial, little f maybe. And so if you take a little f, some non-zero polynomial, we proved this theorem. It was sort of collecting a lot of little results that we proved about irreducibles and primes in principal ideal domains in this particular example fx. If you give me a non-zero polynomial with coefficients in a field f, then the following 5 statements are equivalent. Here are the 5 statements, 1, 2, 3, 4, 5. F is a reducible polynomial if and only if the ideal that it generates is a prime ideal, if and only if when you quotient by the ideal generated by f, you get an integral domain, if and only if the ideal generated by f is actually a maximal ideal, if and only if when you quotient by the ideal generated by f, you get actually a field. So in particular, if you give me a irreducible polynomial, little fx in capital Fx, irreducible, recall, means that you cannot non-trivially factor it. If you give me a reducible polynomial, then when you take the polynomial ring fx and quotient out by the ideal generated by little f, this quotient ring is actually a field. And we also saw that you can actually identify f, the field that you started with, as a subfield of this field K. It's not literally a subset, but you can identify it with a subset of K via sending a constant R, constant here means elements of F, to the corresponding coset in Fx mod Fx. So taking R to R plus the ideal generated by F. Yeah, so you can think of K as a field containing F. And these fields are studied in field theory in the subject of extension fields. And I want to just look at a few examples, but before that, let me just give some description of K in general. So we want to, and again, this lemma, this was already discussed when we were giving examples of quotient rings, but here I'll give more details. And for this one, I'm not taking a reducible polynomial, I'm just taking some positive degree polynomial. Let fx in capital Fx, capital F is always going to be a field. And if you want, just assume that f is real numbers or rational numbers. The set of rational numbers would be a good example. Let fx be a polynomial of degree at least 1. I'm going to call the degree n. Then for each element in the quotient ring, so I still want to, so the object I want to study is this quotient ring, fx modulo the ideal generated by this polynomial little f. For every element in this quotient ring, there exists unique polynomial R of degree less than or equal to n minus 1. Remember, n is the degree of the polynomial little f that you're quotienting by. So if you quotient out by a degree 5 polynomial, then you can always find a unique polynomial of degree at most 4 such that this element of the quotient ring is represented by that polynomial. In other words, if you denote the polynomials of degree strictly less than n by this symbol, so this is elements of set of elements of fx of degree less than n. Let's make that notation. Then from that set to my quotient ring, I have a map given by continued alpha of r equals r plus f is a bijection. So for example, if you take, I don't know, qx, and if you take so f is q, and if you take little fx equal to x squared plus 1 or something, okay, then the elements of this quotient are exactly elements of this, are all look like this, where a and b are rational numbers. So all degree 1 polynomials, degree 0 or degree 1 polynomials. Yeah, so for each pair of rational numbers there is an element in the quotient ring. So this lets you list the elements of the quotient ring in a standard manner. Yeah, if you had a cubic, maybe something like that. Let's not use the same letters. Just giving examples. Then the elements of the quotient ring are in bijection with all expressions of the form all degree 2 polynomials at the most, because you're quotienting by a degree 3 thing. Yeah, so for every, you give me a triple of complex numbers and I'll find an element in the quotient ring. And if you give me two different set of triples, two different triples of rational numbers, rational numbers. If you give me a triple of rational numbers a, b, c, I'll give you an element in the quotient ring, this one. And if you give me two different triples, a, b, c and a prime, b prime, c primes, then the elements in the quotient ring are going to be different. So that's a way of listing all the elements of the quotient ring. I'll talk about examples in a bit again, but let's just go through why this is true. So scratch off proof. And in the next videos, we will take some concrete examples and unpack this lemma. So let us take an element in the quotient ring. What's my job? I need to find a polynomial r of degree at most n minus 1 such that k is equal to the coset of r, right? That's what I want. So what does k look like to begin with? It's an element of this quotient ring, so it's a coset. K is coset of some polynomial g. This g does not necessarily work because g can have some high degree. I need a polynomial of degree at most n minus 1. So what you do is you divide g by f. So by using division with remainders, we can write g equal to f times another polynomial plus another polynomial where q and r are polynomials and degree of r is strictly less than degree of f, which is n, which means r has a degree at most n minus 1, you see. And now note, observe that this R is a multiple of F minus G, or the other way around, right? Oops. G minus a multiple of F. Let's put it this way. G minus R is a multiple of F, so it's in the ideal generated by F. So the coset of G is same as the coset of R. So K, which was by definition the coset of G, is actually the coset of R. So now I have found a polynomial of degree less than n such that K is the coset of that guy. So that proves the existence part, this part, the existence part of R. And now to show that it's unique. So this proves existence of R. And now I suppose you have two things like that, and so uniqueness. For uniqueness, what do I say? So say K is an element of the quotient ring, and you write K equal to R plus F, but also equal to R1 plus F for some R and R1 in Fx, both of degree strictly less than n. So we have a notation for that. Fx less than n. Yeah. So we have two polynomials of degree strictly less than n such that K is equal to the coset of R, but it's also equal to the coset of R1. What does that mean? That means R minus R1 is in the ideal generated by F, i.e. it's a multiple of F, that is, F divides R minus R1. But now you have a problem because this guy has degree n, and this guy, both R and R1 have degree less than n, so the difference also has degree strictly less than n. Let's put it like this. Degree less than or equal to n minus 1. And a degree n polynomial, if it divides a polynomial of strictly lower degree, then that lower degree guy has to be 0. Because when you divide, what does that mean? That means that this polynomial here is a multiple of f. But a multiple of f has higher degree. So the only way it can have lower degree is that if it is 0. So this implies R minus R1 is 0. So R equals R1. So which means that if you give me a K, there is only one R of degree strictly less than n that I can find, such that K is R plus F. So this proves uniqueness. Okay. So again, to give an example, quick example, which we also saw last time, if you take Rx as your ring, and this is a reducible polynomial, for example, we saw, then if you take Rx mod the ideal generated by F, that is equal to all these cosets. So for each pair of real numbers, you have an element. Each ordered pair of real numbers, you have an element of this quotient ring. So just as a vector space, so this becomes a real vector space. And a real vector space, this is just nothing but R2. And we saw, really, this is a field, and this is actually isomorphic to C. So we know that C as a vector space is just R2. That's what this is saying.